Log on, tune in, find out. Another good idea from Cambridge.
Session of our little workshop, and Hervé Chauris back in seismic.
Exactly. Yeah. Thank you. Thank you for staying, especially because this is my second talk. So thank you for the organizer to give you the chance to give a second talk. Well, that talk is different compared to the talk I gave on Wednesday, and at least for two reasons. First one is that this talk is more devoted to modeling rather than inversion, but you will see that within the topic I try to present some inversions. Second reason is that I decided, instead of having a nice talk from alpha to omega, I would say, with a nice pictures and so on, I decided to extract from an ongoing project some questions we face where we do not have answers. So in fact, I put in purples everything that is going to be written in purple are questions for which I do not have answers. And in fact, for some questions, I think they are really easy answers. But let's say I'm here, so I take the opportunity to present that work. So in fact, this is an ongoing work with two PhD students, Sebastian Pence and Elise Vinibar, and this is just part of their work. Okay, so the objective is to derive a scheme, numerical scheme, and here a finite difference scheme on unstructured grids, and that scheme will be applied on electric and seismic modeling. So it's a bit strange, because why coupling finite differences with unstructured grid? So I try to give some answers during the talk. So what do I mean by unstructured grids? Well, it's very simple. Here on the left hand side is an example of a grid, so just a regular grid, and about the same grid but unstructured mesh or grid on the right hand side. So if you need, especially on seismic, on electrical imaging, to incorporate topography, here is a smooth topography, you may think at more complex topography, then you really have to take into that into account, and that could be a key point. And also sometimes you may want to introduce some interfaces at some positions. You may want to refine the grid around some points or some positions. So the mesh is could be quite important. So to go into more insights, well, I would start with electrical resistivity modeling. In fact, we would like to solve this Poisson equation with some Dirichlet or Neumann boundary conditions. So it's very simple in a sense, and I just here mention a few difficulties we face. So let's go on that one. One is a strong resistivity contrast we have in the Earth, and typically if we think about acoustic velocities, P waves, we have a contrast between 1 to 5 or 1 to 10 maybe in some situations, but for the conductivity, contrast is between 1 to 1,000 or 1 to 10,000, what we observe in the Earth. Of course, we have an elliptic equation, so we know that the potential, depending on the source you have, but the potential could be continuous, so we take that into account. Second issue that we have is that we have a source singularity here, especially if we represent that source as a Dirac point. So in practice, you have 4 electrodes, you have 2 sources, 2 receivers, and you combine them to have some apparent resistivity. But when you try to model this kind of source, then you end up with a singular functions around the source. So you have to do something about it. And what people usually do is that they decompose the potential into 2 parts, the part with a singular part, another one basically with a non-singular. It's not necessarily smooth, but a non-singular part. In practice, you do 3D modeling, but sometimes when you would like to get fast results, you would like to do 2D modeling. But of course, you have to properly model amplitudes. So you have to do what I call 2.5D modeling. So basically, you extend your model in the 3rd dimension, and you solve your equation just with a 2D code. And to do that, you could do a Fourier transform over the third dimension, so it's very classical, and you have to do it a number of times, and then you integrate all these contributions. And finally, you would like to take into account these arbitrary geometries, and this is why we went to unstructured mesh. So this is very classical. So if you stay within the finite difference code, and if you would like to take into account interfaces like these that do not necessarily align within the grid here, well, in fact, it's still possible. And there are works by Lévesque, or more recent works by Lombard in Marseille, where in fact they introduce this interface, like a floating interface, and they add some conditions around this point. In this region, you have a classical finite difference scheme, but in between, you need to add like a jump conditions. That work has been extended to non-smooth interfaces, like here, by Yu and Al quite recently. And you could do it in 3D, but of course you have to realize that you have to know in advance where the interface is. So if this is topography, then it's okay, but if you do inversion and that the interface or the major contrast moves during the inversion, this could be more complicated. Okay? But nevertheless, it's possible in 3D, but it's a bit tricky because in 3D you have to know is my point on which side of the interface my point is, and then you need to have at least one point on the other side. So on this edge, it's a bit tricky. So what we have done is very simple, is that we use this approach, but here was a contrast line exactly on the grid. So we modified the grid, and we took the same sort of jump conditions that were possible here to introduce these on the unstructured grid. So this is our initial equation, and it's possible in the scheme to have jumps in potential and to have jumps in the normal derivative. But for the simple case where there is no jump, that equation simplifies to something like this, where here we consider the central point and here neighboring points. In fact, we do not really have to consider a mesh, but for simplicity, especially to define where the conductivity is, this is much easier. Other people consider just a cloud of points. Okay, so here is a weight around the central part, and here is a weight for other points surrounding where this point. So if you have jumps in the potential or here, then the formula is a bit more complicated. So what are my alpha points where there are some sort of a Laplacian point, and this is where finite differences come up. So basically what we do is very simple. To find the derivatives, we estimate the derivative through a simple Taylor expansion around the central point. So this has been done, for example, recently by Gavete et al. So in fact, we minimize this. We try to find optimal points. So what we would like to estimate is a u vector. So this is the value of the function, the first derivative in space, and the second order derivatives. From what? From the value of the function at different points. So 0 to p, this is my points here. And here we have, for example, in 2D, we have 6 unknowns, and we have a number of points around the central point. So this A matrix has all the distances between the central point to other points, and we simply solve this kind of equation. So if I go a bit further on that, what you simply really realize, and what I just said, is that you need at minimum 6 points in the stencil to be able in 2D to derive your 6 unknown. So you are looking for the function value and its derivative. So in 2D you have 6 unknowns, and in 3D you have 10 unknowns. So does it work with the classical mesh? Well, the answer in 2D is yes, and the answer in 3D is no. So what happens in 2D? Here I have a mesh, okay? It's not really easy to see, but here what I did in the upper part, I plot the number of points within the distribution of number of points in the stencil. So what I expect is to have at minimum 6 points. So it's difficult to see maybe from the back, but here the peak it has 7 points. So this is mean value. Here we have 6 points, and we don't have any energy for 5 points. So if I use that mesh, it works fine. If I go to another, to the same mesh, but with different parameters to generate the mesh. So here I use a G mesh here. In fact, for few points, maybe 1/100, I have some points where I only have 5 connections. In fact, 5 points is the stencil. So this is not enough. But in fact, there are options to have at least 6 points in the stencil. So it does work in 2D. What happens in 3D, here is just an example. So here's a sphere. So I meshed first a 2D sphere, and then I meshed inside. I put some constraint saying that the mesh should be refined around that point and should be quite large here, just to an indication. And then in 3D, you have different options depending if you use a Delaunay triangularization or something different. And in fact, you have plenty of options. And here, as before, I displayed the distribution of the number of connections in the stencil, and here's a distribution, the percentage. So in that case, the mean value is about 20. Here, the mean value is about 15 connections. Well, what I have is that for a number of points, I do not have the minimum 10 value, but I have 8 or 9. Okay, that is not good for the purpose. For Delaunay triangularization, this is better, but in fact, it does not always work. So most of the time it works, but in some cases, so here, for example, depending on the constraint, you put here. Here I have a few points. It's about less than 1% with stencils with only 9 points in the stencil. So with 9 points, you can't solve for the derivatives. So you need additional points. So my question is, so it should be written in purple, but here it's written more or less in dark red. So is it possible to find a suitable mesh in 3D where I have enough connections? So I didn't have the answer. Well, I go one step further. I try to estimate the u, so this is a function and its derivative at the central point from function from the estimated value. And basically later, in a simple case, but in other case, I will have to have I have an estimation of my Laplacian. And basically this is alpha naught at the central point plus other points. If I have more than 6 points in 2D or 10 points in 3D, and this is usually the case because the mean value is around 15 in 3D and the mean value is around 7 in 2D, then I have different possibilities to estimate these derivatives. So what I put, I solve a least squares problem, but I may play with these weighting factors. And it appears just by trying, by testing, that factor is quite important. So here I put it as a diagonal matrix with and I would like to find my optimal weights, W, so that, for example, I have the best condition number for this little matrix. Okay. And of course, I would like to respect some constraints. So for example, for the Laplacian, I would like that the central weight is negative and all other weights are positive, like 1, -2, 1. So, okay. So, is there an optimal solution? Well, I don't know. Okay. So this is some sort of inverse problem we face. I don't know. Last is about the shape of elements. I'm constructing this grid, this mesh. What about the shape of the element? Well, I did a very simple exercise. Here, look at the red point here in the middle, and I'm constructing, I have a parameter gamma that is between 0 and 1. Gamma equal to 0 means that this point that is going to move is at this position. Gamma is equal to 1 means that the point is at this position. This position is exactly between two green points. So it means that the triangle, that triangle is flat. Okay, surface is 0. Measure of the surface is 0, and we have a gamma parameter between 0 and 1, where I distort, I modify my mesh, and I do a simple experiment. Well, I'm solving the Poisson equation for a simple case where I have here Dirichlet conditions. The exact solution is a third order polynomial function. Okay, this is the exact solution after inversion, and with a finite difference scheme, I have a solution that is at 10 minus 5, so it converges. Okay, and this has been obtained for my reference grid. By reference grid, it's gamma equal to 0. This is this grid. Okay, I do the same with a finite element code. Okay, so structure is not this. Structure of the code is different, but the residuals are quite small, 10 to the power minus 4. But the structure of the residuals are not the same. Okay, and what I simply do is that I compute, or an estimation, or compute the condition number of my system. So when I solve the system, when I solve my initial condition, that one, I say, okay, I have to solve f multiplied by my potential is equal to b. So, and what is the condition number of my capital F, my forward modeling? Okay. So it does evolve depending on my gamma function, but in fact, for this case, it's more or less the same. It's around 3, so in fact, it's a log of 10, so it's around 1,000. And you have an increase, okay, and then a decrease, a slight decrease. In fact, the maximum is about 10% higher. So in fact, that scheme does work even if you may have some flat triangles. And why does it work? Because in fact, you have for sometimes more triangles. So even here, when I would like, let's say here, I would like to estimate my derivatives. I have 2 points aligned, but I take the distance into account, and finally, I'm able to estimate my derivatives. Okay? If you go to a finite element scheme, while the condition number increases and could be as large as you would like to have, of course, when you have a flat triangle. Because at some points, it's obvious, but you divide by the measure of the triangle. Okay? So maybe you could do better things, but okay.
Sorry, I don't understand. What condition number are you talking about in the case of finite elements? Because I see you invert a matrix to find the weights for your finite difference scheme, but what is the condition number in the finite element case?
Okay, so in fact, I'm referring to this equation. I try to solve there are two levels. In the finite difference scheme, there is a local level where I try to estimate my derivatives. So this is exactly here. And then once I have these derivatives, then I need to find my potential. So, and for the potential, I solve this equation.
Oh, in both cases, it's the overall condition number of this matrix.
Exactly.
Okay,
yeah.
sorry.
Yeah.
Thanks.
No, I'm sorry. So I try to solve this equation. F is for the forward modeling, and the condition number I was displaying just before is the condition number of that operator. Okay, so in this simple case, I had a limited condition number, but is it possible to prove that whatever the mesh, my condition number is limited? And but of course, you have some possibly some conditions that you need to have enough connections, and possibly you don't want the red dot to be exactly on a green dot. Could be maybe in between, but not this. And that would be a way to handle flat triangles. Okay, so this is just questions I have. I just here show a few examples of modeling in electrical domain. So in practice, what you have to do is that you have to extend the domain, because to handle properly Dirichlet conditions, here we put 0 here and the main condition at the top, and here's the central part where you are interested in, and in fact it's just a small part in here. So I go here, I give you just an example of how you could do it and what you have, and here you see that the isochrones are perpendicular to to the top. This is a solution. In fact, it's a secondary potential for a source that will be around here. So you could check, I skipped that one, maybe here. You could check the validity of the scheme. So we studied also the convergence. And you see that I superimposed the analytic solution to what I have obtained, to the numeric solution. You see some little differences. So what it is, this is for a constant spacing between electrodes. So you have 4 electrodes, and you have a constant spacing between different electrodes, and you move electrodes from left to right. So you have different potential, different apparent resistivity, and this just to check if it works or not. Okay, you could do the same in 3D. And here I compared with analytic solution where I have a contact in 3D. And if I make a zoom in that part, here in red I have the analytic solution, in blue I have the 3D solution, and here in black, in purple, I have the 2.5D solution. And for 2.5D you had to do a number of times the 2D solution. So that's why in fact the 3D better converges. Okay, I would like to spend a few minutes on the seismic part. So about the seismic part, the idea is really the same. So we have studied on unstructured mesh what the stability conditions are, what the dispersion condition is. So that would be possible to handle topography and maybe internal interfaces, as I said. But also, sometimes we would like the mesh to be distorted. And why? Like say, if you have a simulation of flow in a porous media where the geometry itself changes with time, not at the time of propagation, but during times, then okay, you would like that the scheme is some sort quite robust with respect to the geometry of the mesh. So here we use simply an acoustic equation in a very simple case, and I just show you this result. So we compared what we get in the case where we have an interface within the model, and it's a bit difficult to see. On the top left, this is with a gridded model, and in fact here we have some little staircase. So here's little staircase. We just use a classical finite difference scheme, and what you could see is that this little staircase, so just one grid point, creates some diffractions with lower energy, and you could see these diffractions around here. So here's a snapshot, so for a photo at a given time, and you have the reflected energy, we have a transmitted energy, and here you could see, in fact, the summation of different diffractions. If you refine the grid, here you take about 4 more points, because you are limited frequencies in the data. Then here you still have this staircase, but you could get rid of this diffraction. For about the same amount of grid points here, but with a grid, with a mesh, so exactly flat, here you have about the same quality as if you would have more elements in your grid. Okay, so here it's exactly flat, and triangles really lie along that interface. So it's just to prove that some sort of benefit if you have a nice description of the interface. Okay, so same, you could handle topography here. So there is no movie, but I'm just moving with my hands. Okay, so okay, and you go back and forth. Okay, and you see that part of the energy is reflected as you would expect. So okay, you could compare with what you could analytic solution or what you expect from this. So talk is quite short. I'm already at the conclusion where I have some questions. In fact, well, we try to develop that scheme. Seems to be a bit strange at the beginning. So in the case of electrical modeling, it's possible to take into account some jumps of the potential. If, for example, the source is a derivative of Dirac, for example. In 3D, we face with the problem that we do not have enough connections. So the easy thing is to go a bit further away and to take an extra point a bit further away. So in that case, you have to decide what would be my conductivity. So maybe you could do mean conductivity, something. So there are there are possibilities, but maybe if that would be possible to have a mesh with sufficient number of connections, that would be nice. This is possible in 2D, but we don't know in 3D. Okay, it appears that playing with the weights, so of the local transform, then weights are important to get a good estimation of the derivatives. Okay, so maybe you could play with optimal weights and about the mesh, and also what we could think is comparing finite elements or finite differences. If we think at longer term stability, for example, on seismic wave propagation, if you do a seismic interferometry, then you have to record data for a very long time, and then you correlate the data. Okay, so is one scheme more stable compared to the other one for long period? Well, this is the question I have. So this is my last slide. I have a few references. You may have a look, and I would like to thank especially Olivier Stab, who helped us around the mesh. Thank you.
Any questions or any answers, in fact, for this gentleman?
Hervé, could you comment on the order of your scheme? And the second thing is that could you comment on the reflection coefficient? Do you model always independently of the mesh the correct reflection coefficient? In one of your comparison, it was unclear that it was exactly the same reflection coefficient.
So about the reflection coefficient, I don't know. The answer, I don't know. But the order of the scheme in space is low. It's order 2, you know. Yeah. So, and if you would like to extend, so we pay more attention on in the electrical system. And if you would like to extend for a larger order or longer order in space, then what happens is that you have a large contrast in conductivity. So in fact, we tried, let's say, to have a second order or fourth order in space, and the result were worse. So in fact, yeah.
Any more points? I had a question. Why are you interested in using flat triangles? Because that breaks all the theorems about convergence of finite elements. In fact, it's quite dangerous to do, because bridges have fallen down because of it. People use a bag. Well, actually, no, it was an oil rig. There's a famous case of an oil rig. One of the legs collapsed because they hadn't spotted some bad triangles in their stress calculations. So why do you want to use a flat triangle?
No, I mean, in 2D it's not a problem, but in 3D, when you construct a mesh, if you put lots of constraint, then you may not have flat triangles, but you may have triangles that could be flat if you impose lots of constraint. So in fact, what I'm referring to be more precise, if you use a spectral elements method, so the finite element method, where you have a really good convergence rate, it does not work on triangles, but it does work on quadrangles. Yeah. And the key issue there is not in 2D but in 3D, and 3D they spend quite some time just to have a nice mesh. And most of the time, just at the edge, for example, of the model, or exactly what you put some constraint, then they have more or less flat quadrangles. So I think for triangles 2D it's really not an issue. But if you bring quite some constraint on the 3D model, then you may have not exactly flat, but a smaller tetrahedral. This is what I think.
One more comment.
One quick remark on your question. Is it always okay to determine the weights of the finite difference generalized scheme? If the points in your neighborhood align along certain algebraic curves, it turns out that you have a bad condition number. It's a conjecture of Peter Olver and Charlie Pfefferman and others. So people have thought about it, but yeah, it's open.
Okay, you may have, in some circumstances, you may have a really bad condition number, especially if you just have 5 connections. Then you may end up with a bad condition number, of course. But if you have enough connection, then you have some sort of a guarantee that you could have a limited condition number.
Right then, so let's thank Hervé.